how do massive infrastructures like, our power grids stay reliable without costing an absolute fortune to monitor every single point? It's a huge challenge, right?
Oh, absolutely. I mean, the cost just for the hardware, installing it, maintaining sensors everywhere, it would be mind-boggling.
Yeah, that really puts the scale into perspective. And that's exactly what we're going to dig into today. A pretty ingenious method for tackling this, specifically for placing voltage sag monitors optimally in power systems. We're talking about where to put sensors on the different buses, those connection points in the grid.
And, this isn't just about your lights flickering at home. A voltage sag, that's a sudden brief drop in voltage, it can have a really significant financial impact.
How significant are we talking?
Well, the sources we looked at estimate damages could get this up to $10 million for industries like semiconductor manufacturing or automotive plants, just from these voltage dips.
Wow, $10 million. From just a brief dip. That's huge.
Yeah.
So, okay, the problem's clear. Sensitive equipment needs protecting, but monitoring every single bus isn't feasible cost-wise.
Exactly.
So our mission for this deep dive is to unpack how this newer, clever approach helps strategically choose where to place those vital monitors, saving money, protecting gear. So now we get the problem. Let's get into the core of this innovation. What makes this method stand out from, say, the traditional ways?
Well, what's really fascinating, I think, is how they embrace uncertainty. Older methods often kind of assumed things were constant, variables affecting sags.
Okay.
But this paper, it takes a different route. It actually considers the uncertainty of those variables. They use something called the Monte Carlo simulation.
Ah, Monte Carlo. Heard of that.
Right. And they use it to build this huge, what they call a trustworthy database. And get this, the simulation runs for a massive 4,000 years of virtual grid operation.
4,000 years? Seriously? That's some serious data crunching.
It really is. They do it to make sure the data is super robust.
Okay, so what kinds of variables are they factoring into this massive simulation? What creates the uncertainty?
Well, all sorts, like the type of fault, for example, single line to ground faults. That's basically when one power line hits the ground, short-circuiting. Those are really common, about 80% of them.
80%, okay.
Yeah. And then fault location, where it happens.
Yeah.
Fault impedance, that's like the resistance during the fault. They model that with an average of 15 ohms. Standard deviation, 4.5 ohms. Also fault time, how long it lasts, when it's cleared, and even the system load at the time.
Right, so it's a whole mix of factors. So once they have this incredible 4,000-year database, what tools do they use to actually pinpoint the best monitor spots?
Okay, so they use two main tools. First is the Probabilistic Monitor Reach Area Matrix, or PMRA.
PMRA, okay. What does that do?
It goes beyond just yes or no did a sag happen.
Yeah.
It actually quantifies the probability of a voltage sag occurring and being recorded at a specific bus given a certain fault.
Probability. Can you give an example?
Sure. Like if a specific kind of sag happens, say 700 times in 2,000 simulated years at a particular bus,
Okay.
the PMRA matrix would assign a probability of 0.35 for that scenario at that bus. So it gives you a much richer picture of the risk.
Got it. So it's not just black and white, it's shades of gray, probability-wise. That makes sense. So what's the second tool they use?
That would be the Pearson coefficient for correlation.
Pearson.
All right.
Okay, correlation. So measuring how related things are.
Exactly. This helps determine how strongly the voltage sag data from different buses are correlated. So if data from a bus you are monitoring strongly correlates with one you're not monitoring,
Then the monitor one can kind of stand in for the other one.
Precisely. It means you might not need a monitor at that second location, saving costs. The source mentions an example like in a 9-bus network, where data from bus 2 showed the highest correlation with bus 1.
Ah, okay. So you leverage those relationships. Pretty clever.
Which brings us to a really crucial takeaway here. With all this probabilistic data and correlation analysis, does it spit out one single perfect answer for monitor placement, like older methods might have aimed for?
Good question. Based on the uncertainty aspect, I'm guessing?
Oh, you got it. That's the aha moment, really. This method shows there's no unique optimal answer.
Right. So it's not a fixed solution.
No. The best placement actually depends on what the engineers want to achieve. Specifically, their desired probability of observability, or POI, like how likely they want to be to actually see a sag if it occurs.
Okay, the POI.
And the correlation rate they're comfortable accepting between buses.
So it's tunable. Like in the I-14 bus system example they used, depending on the POI and correlation targets you set, you might end up needing monitors at, say, buses 10, 13, and 14.
Right.
Or maybe under different targets, it's just buses 10 and 14. It adapts.
Exactly. And it's interesting, the inherent maximum observability you can achieve varies a lot too. That 14 bus system might top out at 0.635, meaning you can only ever observe about 63.5% of SAGs probabilistically.
Whereas a bigger 57 bus system might reach 0.94. Wow.
Yeah, so the network structure itself plays a big role. It really highlights the adaptability.
So, wrapping this up then, what does this all mean for you listening? Well, this method offers a really cost-effective, robust, and crucially adaptable way to watch over critical power systems. It smartly uses probability and correlation to protect against those costly voltage sags.
And it makes you wonder, doesn't it? How could this kind of sophisticated approach, using probabilistic data, understanding correlations to optimize where you put resources, how could that apply elsewhere, beyond just power grids?
Yeah, great point. Where else might understanding uncertainty and how things connect totally revolutionize how we make decisions? Definitely something to chew on until our next deep dive.